You are listening to The Vocal Technologist. Spoken tech for your ears.
Have you ever just stood in a busy local cafe and just watched a really efficient barista handle a massive queue of incredibly intricate coffee
Oh
orders?
yeah, it is bizarrely satisfying to witness.
Right, because they have got three different types of milk steaming at once. They are pulling shots, taking new orders, wiping down the counter, and they just effortlessly switch between all these tasks without breaking a sweat or...
We're wasting a single movement.
Exactly. It is just flawless, continuous motion.
I reckon it is the perfect real-world metaphor for a highly optimized system, really.
Yeah.
It's elegant engineering in human form, where, every single bottleneck has been meticulously ironed out so that the throughput is absolute maximum.
Spot on. It is absolute poetry to watch. And that idea of elegant, frictionless engineering is exactly what we are going to explore. You are tuning in to Product Thursday's Data, part of the Vocal Technologist. We are going to unpack the absolute bleeding edge of data architecture and artificial intelligence systems.
We have got heaps to get through.
We really do. We are going to look at extreme architectural optimizations from massive tech companies, the harsh reality of deploying artificial intelligence agents in production environments, and how base layer tools are being pushed to absurd new speeds.
And we are not just looking at incremental updates here. We are examining fundamental shifts in how data is stored, queried, and understood by machines. As you listen along with us, I want you to really think about the systems you interact with every day. Are they built for the future, or are they just patching over the cracks of the past?
Let us get straight into it. Speaking of extreme efficiency, let us look at what happens when massive tech companies realize their foundational systems just cannot scale anymore. Take Netflix, for example.
Classic example of operating at an incomprehensible scale.
Exactly. But they recently managed to drop the CPU utilization of their Ranker service, specifically for their serendipity scoring feature, from 7.5% down to around 1% per node. That is a massive drop for a company of that size.
What is genuinely fascinating there is the underlying mechanics of how they achieve that drop. Because it comes down to fundamentally re-architecting their scoring logic. They transitioned away from using scalar dot products and moved to batched, cache-friendly matrix multiplies using flat buffers.
Okay. For anyone who might not be deep in the mathematical weeds, what does that actually mean in practice?
Think of scalar dot products like moving 100 heavy boxes across a warehouse. By picking up one box at a time, walking it over, and coming back, it processes numbers sequentially.
Right. Very slow.
Very slow. Matrix multiplication, especially when batched and cache-friendly, is like putting all 100 boxes on a massive pallet and using a forklift to move them all at once. To make this work, they leveraged the JDK Vector API. This allowed them to achieve pure Java SIMD performance gains.
And SIMD stands for single instruction, multiple data, right? Meaning the processor can execute the exact same operation on multiple data points simultaneously, just like that forklift moving the whole pallet.
Precisely. By doing this in pure Java and eliminating unnecessary memory allocations, they saw a 12% latency reduction and a 10% improvement in CPU per request per second. What Netflix is proving here is that at a certain scale, general-purpose computing is dead. You have to mold your software to the physical shape of the hardware.
Seeing Netflix squeeze that much performance out of their servers really makes me wonder about high-stakes search infrastructure. Because I use GitHub every day, and if that search bar goes down, my entire workflow just completely stops. And they completely rebuilt their search architecture for high availability.
They absolutely rebuilt it from the ground up. They utilized Elasticsearch cross-cluster replication. What they did was run independent single-node clusters per instance, completely separating the primary nodes and the replicas.
Which ensures incredibly durable persistence.
Spot on. But the really clever part is that the asynchronous replication is triggered only after Lucene segments are created.
Let us pause on Lucene segments for a second, because I reckon that is a crucial detail. Why wait for a segment to be created?
Because replicating every single tiny keystroke or minor index update creates a massive network overhead.
Oh.
A Lucene segment is essentially a solid flushed chunk of immutable data. By waiting until a solid chunk is formed before sending it across the network, they save a tremendous amount of bandwidth and processing power.
And the practical outcome of that brilliant data flow is zero downtime migrations. They also built in automatic replica promotion. So if a primary node catches fire and fails,
The replica just takes over instantly.
exactly. The failovers are entirely seamless, and the developer searching for a repository never even notices a blip.
If we connect this to the broader industry picture, it is all about decentralization. Which brings us perfectly to Uber. They had a monolithic Hive data warehouse that was becoming a massive bottleneck. Having every single engineering team dumping their data into one giant centralized repository is a guaranteed recipe for gridlock.
It is like trying to force all the traffic of a major city through one single intersection. So they decentralized it, they implemented database federation, migrating datasets into smaller domain-specific or team-owned databases. But my question is, moving that much data usually means massive downtime, right? How do they pull that off?
They engineered a custom bootstrap migrator. It allowed them to copy data to new locations without data duplication or any system downtime. But the real magic was keeping the metadata consistent across all these new, smaller, independent databases. To do that, they used Apache Flink to maintain real-time consistency bidirectionally.
Bidirectional, meaning if a change happens in the old monolith, it updates the new database, and if a change happens in the new database, it updates the monolith, ensuring zero data loss during the transition period.
Exactly. It raises an important question for you, the listener. Consider your own organization. Are you clinging to massive monolithic systems out of habit when domain-specific decoupled architectures clearly win at scale? It is a hard transition to make, but the efficiency gains are undeniable.
That transition reminds me of the broader complexity we see in modern data stacks, especially when artificial intelligence steps in. Because we're not just dealing with databases anymore, we are dealing with AI agents trying to talk to those databases.
And that introduces what we can call the fractal complexity of the modern data stack. For years, the industry has added endless layers of tools designed for ease of use. But instead of making things simpler, they have created departmental silos and a culture of decision avoidance. People rely on the abstraction layers of the tools instead of actually understanding the underlying business logic.
Which is a perfect segue into the failures of chat BI systems. The idea is brilliant on paper. You just ask a chatbot a plain English question, and it writes the SQL query to get your data. Empirical testing using the BIRD and DABstep benchmarks shows these agentic chat BI systems hit over 70% accuracy on SQL generation.
That is right.
Hold on, though. If they are hitting 70% accuracy, does that mean data analysts are basically out of a job, or is there a catch?
There is a massive catch. 70% sounds great until you look at where the failures actually happen. They completely break down on ambiguous metric definitions and common sense gaps. Let us say a chief executive officer asks the AI for active users. The AI does not inherently know if that means users who just logged in, users who actually made a purchase, or users who spent more than 5 minutes on the site.
Right. It is the classic problem where you ask 3 different departments for the sales numbers and you get 3 completely different spreadsheets back. And I see engineering teams try to fix this by slapping a giant rules text file on top of the AI, just hoping it will read the rules and learn the context.
Which is a terrible strategy, straight up. Adding rules files just creates compounding errors and overfitting. As the business complexity grows, the AI just gets more and more confused by its own conflicting instructions. The actual solution here is semantic engineering.
I want to break down semantic engineering because it sounds like a corporate buzzword, but it is actually critical infrastructure.
Think about traditional data models. They strip away all the business meaning. They just store the raw numbers in columns and rows. That leaves the AI to completely guess the context. To fix this, you need a clear ontology. You need a structured map of cause and effect and strong semantic engineering to make the data truly machine-ready. The AI needs to understand how the business actually works, not just how the database tables are joined together.
And this leads to a broader phenomenon we are seeing across the board, which is agentic AI amplification. These AI agents accelerate code writing, but they just amplify the existing maturity of the team using them. Strong engineering teams get faster because they know what good code looks like and they can review it. But weak teams just generate more bugs at the speed of light.
The bottleneck in software development has fundamentally shifted. It is no longer about the physical act of writing code. The bottleneck is shifted almost entirely to testing, security, and governance. If your AI agent can generate 10,000 lines of code in a minute, you still need a human or another system to verify that it actually works securely.
Since we are unpacking AI bottlenecks, we definitely need to talk about latency. Because waiting 30 seconds for an AI to fetch data and write a response is an absolute eternity in software time.
And that brings us to the concept of zero-waste agentic orage, or retrieval augmented generation. There is a brilliant 2-tier caching strategy being deployed that slashes response times from roughly 36 seconds down to mere milliseconds.
36 seconds to milliseconds. That is like our barista from earlier. Instead of asking for your intricate coffee order every single morning, they just see you walk through the door and immediately hand you the perfect cup. How does that caching actually work under the hood?
It combines two distinct layers. First, you have semantic caching, which is embedding-based. If a new user query is 95% similar to an old query, it does not even bother the AI model. It just serves the cached answer instantly.
That makes sense.
Yeah. The second layer is retrieval caching at the context level, which handles queries with about 70% similarity by reusing the background documents that were previously fetched.
But caching is notoriously difficult because data gets stale. You do not want the AI serving yesterday's financial numbers just because it was a similar question.
Which is why they use timestamp checks and SHA-256 fingerprinting to solve data staleness and handle cache invalidation. If the underlying source data changes, the cryptographic fingerprint changes, and the cache clears itself automatically. This architecture not only makes the system lightning fast, but it cuts language model token costs by over 30% because you are not constantly querying the expensive model.
That is incredibly smart. But even with great caching, the underlying vector databases have physical limits. When you build these RAG systems using HNSW vector scaling, things start to break at a certain scale.
Yes, HNSW stands for Hierarchical Navigable Small World, which is a very popular algorithm for vector search. What is fascinating here is the structural limit. When these systems exceed 100,000 vectors, the latency grows superlinearly. At the exact same time, the recall accuracy completely plummets.
Why does the accuracy plummet just because there is more data?
Because of local minima traps and a mathematical phenomenon called high-dimensional hubness. Imagine a massive city roundabout where all the roads lead in, but it is incredibly difficult to find the exit. In high-dimensional vector space, certain vectors act like massive hubs, pulling in the search algorithm. The system gets stuck in that gravity well, returning highly similar but completely irrelevant results.
So what is the fix? You cannot just tell a growing company to stop adding data to their AI.
You have to apply sophisticated mitigations. This involves tuning parameters, using a hybrid two-stage retrieval where you do a broad, rough search first, and then a precise re-ranking afterwards. It also involves applying quantization to compress the vectors and reduce their memory footprint. It requires serious, dedicated engineering.
Speaking of serious engineering, let us get into code mode tooling, because the standard way we have been using AI agents is having them call multiple tools sequentially. The agent asks a tool a question, waits for an answer, asks another tool, waits again, and so on.
Which is incredibly inefficient and prone to timing out. Code mode completely flips that pattern. Instead of the language model calling tools sequentially over a network, it writes and executes a script in a secure sandbox to compose all the tools at once.
So it just writes its own custom computer program on the fly to solve your exact problem in one single sweep.
Precisely. And why this matters is that it drastically reduces context window bloat and round-trip network overhead. It makes large tool catalogs far more scalable and efficient to operate.
Looking at all these workflow optimizations leads us perfectly to raw, unapologetic speed at the base layer. Because at the end of the day, no matter how smart your AI is, everything runs on a database engine.
And we are seeing massive innovations in the engine room. Let us look at the PostgreSQL Blink tree implementation for high concurrency B-tree indexes.
For those who might need a refresher, a B tree is essentially the internal filing system databases use to organize data so they can search it quickly. But what makes a Blink tree so special compared to a standard B tree?
It is the brilliant simplicity of adding a right link pointer between sibling nodes and a high-key boundary marker. In a traditional B tree, if you are searching for a record and another process is simultaneously writing new data, the database has to hold locks across multiple levels of the tree to prevent data corruption.
Which creates a massive traffic jam. It is like stopping all the cars on a highway just to let one new car merge.
That is a great way to picture it. But the Blink tree lets searches move quickly to the right sibling, using that special pointer without holding locks across multiple levels. It is like adding an express lane on the highway, where searches can bypass the traffic jam of data being written without having to stop at every toll booth. It completely avoids lot coupling during reads. The result is a dramatic reduction in lock contention, allowing massive concurrency.
And it is not just the databases getting faster, it is the parsers reading the files too. Let us talk about the Hardwood Parquet parser. It is an open-source Java 21+ parser that is doing multi-threaded reads. The statistics on it are frankly absurd.
They are staggering. We are talking about reading massive analytical data sets at speeds that were previously thought impossible for pure Java.
Try reading 9.2 gigabytes, or 650 million rows of data, in 1.2 seconds on 16 cores.
And it achieves that mind-bending speed by using page-level parallelism, adaptive prefetching, and direct memory mapping. It does not just read the file sequentially, it breaks it apart and reads multiple pages simultaneously. It is an absolute masterclass in squeezing every last ounce of performance out of modern hardware architecture.
Okay, what about Spiral DB and their cascading compression? Because dealing with highly skewed data is a massive headache for data engineers.
Spiral DB Vortex approaches this with a recursive, data-driven method. Instead of applying a single fixed codec to an entire column of data, it evaluates different encoding schemes on a 1% sample of the data.
So it is like packing for a trip and using different packing methods for your clothes versus your fragile electronics instead of just wrapping everything you own in one giant roll of bubble wrap.
Exactly. It finds the best greedy path and recursively compresses intermediate outputs based on the actual shape of the data. It handles skewed or mixed data beautifully without relying on a rigid, one-size-fits-all approach.
So what does this look like when you put all these high-speed principles together at massive scale? Let us round out these examples with Tencent Games. They are running real-time analytics for millions of concurrent active game sessions. Millions of players generating millions of events every single second.
To handle that kind of fire hose, they're using a fascinating architecture built on event sourcing and CQRS principles. CQRS stands for Command Query Responsibility Segregation, which fundamentally separates the read operations from the write operations.
Which keeps the traffic jams to a minimum, just like we talked about with the blink tree.
Correct. They use Apache Pulsar for high-throughput ingestion of all those rapid-fire game events. Then they use ScyllaDB to fan out those events to millions of specific user sessions. By partitioning events via session IDs and using cross-region replication, they ensure low-latency operations globally. It is an incredibly robust way to handle real-time risk monitoring and in-game moderation without ever slowing down the actual gameplay for the user.
So wrapping all of this up, we have covered pure Java matrix math, speeding up server instances, massive database decentralization with zero downtime, AI agents writing their own sandbox code to avoid network lag, and databases avoiding log contention with express lanes. The overarching theme here is incredibly clear.
The industry is moving entirely away from stacking generic, easy-to-use tools on top of each other. The focus is shifting to building highly tuned, context-aware systems that respect the physics of the hardware they run on.
It is all about intention. You cannot just buy an off-the-shelf artificial intelligence model, plug it into your messy data warehouse, and expect it to magically understand your bespoke business logic. You have to engineer the semantics, and you have to engineer for speed.
And that leads to a final thought I want to leave you with. We have talked extensively about speed, efficiency, and architectural elegance today. But consider the physical and environmental footprint of all this compute. If artificial intelligence queries are getting so dense that we have to invent new ways to compress vectors just to stop servers from buckling, and if we are running millions of real-time game events through global data centers, at what point does our data architecture become less about writing clever code and more about managing grid power and physical energy consumption?
That is a brilliant point. Are we just building faster software, or are we demanding more from the physical earth to power these milliseconds of convenience?
True engineering elegance might not just be about reducing latency. In the future, it might be about understanding the energy cost of every single query you write.
The energy cost of a query. That is definitely going to stick with me. Thank you for exploring all of these complex concepts with us. We really hope this gave you some practical, deep insights into where the architecture of the web is heading. Be sure to subscribe to The Vocal Technologist for more analysis into the mechanics of modern technology. Until next time, keep optimizing.
Spoken Tech for your ears.